ideas and concepts of limits to determine what it means for a function to be continuous at a point. Maybe even encountered continuity in prior classes before. However, this is going to be looking at from a more rigorous definition. So developing the notion of continuity, perhaps you've encountered different types of discontinuities before in Algebra 2. So we'll start with the different types of discontinuities: removable, jump, and lastly, infinite/vertical asymptotes, okay? So we'll use each of these cases to evaluate what it means for a function to be continuous at a point, okay? So if we look at case 1, we can see that our function is not continuous here because what our function value is at x equals a is not what does not fit in with the trend of our curve, okay? So for something to be continuous, we think of something that has a flow that doesn't break. We can see a break right here because we follow this nice flow of our curve and then we jump up. So in our first case, we can say that our function is not continuous because if we note the limit as x approaches a, if we follow the trend of this curve right here, is not equal to the function's actual value at x equals a. So the limit not being equal to the function's actual value at x equals a breaks the continuity. If we look at our second case here, okay, we see that our function value does exist, but we see there's a break right here with this jump discontinuity, specifically because our limit as x approaches a from the left side is not equal to the limit as x approaches a from the right side. We have different values. So we can say in the second case is a limit not existing at x equals a breaks the continuity of the function. Again, the limit does not exist because the limit from the left side does not equal the limit from the right side. Lastly, if we look at our third case here, we see we have a infinite discontinuity/vertical asymptote. We can see that occurs because our function does not exist at x equals a. We don't have a value here, nor does the limit exist. So we can say in the third case, the fact that f of a does not exist breaks the continuity of the function. And you could also extend this to the limit as x approaches a does not exist as well, but we're more going to be focused on f of a here not existing for our purposes. So again, to summarize, in the first case, the limit, we don't have a continuous function at x equals a because the limit is not equal to function's actual value. In the second case, the limit not existing at x equals a breaks the continuity function because the left-handed limit is not equal to right-handed limit. And in the third case, f of a just straight up does not exist. So using these observations, we can formalize what we need for a function to be continuous. So the conditions for the continuity of a function is that f is continuous at point x equals a if and only if f of a first exists, aka plug and chug x equals a into the function. Okay? So that means we just straight plug and chug, we don't do anything fancy. Now we move on to step 2. The limit must also exist, okay? The limit as x approaches a must exist for f of x, which requires us to either use the limit methods from 1.2 if we're dealing with rational functions or square root functions, or if we have a piecewise function, we have to use the left-handed and right-handed limit concepts from 1.1. And then the third step is we need that the limit agrees with what the function actually is at that point. So we require that the limit as x approaches a of f of x is equal to f of a, which requires us to compare the results from step 1 and from step 2. Please note that each condition must be met for a function to be continuous at a point. If any one of these conditions is not met, then the function is not continuous at x equals a. So if 1 and 2 are met, but 3 is not, we do not have continuity. And it's advised that you follow these steps in this order in order to be most effective with evaluating continuity. With that said, we can also classify the types of discontinuities that we've been looking at, okay? So a jump discontinuity occurs with strictly a piecewise function, and it occurs because the left-handed limit does not equal the right-handed limit, okay? So if working with a piecewise function and you notice that the left-handed limit is not equal to the right-handed limit, then you have a jump discontinuity at that point. A removable discontinuity occurs because f of a does not exist, like we see right here, but the limit exists, okay? Or, as we saw on the first slide, we have f of a could be a closed dot above our function here, but f of a does not equal what the limit as x approaches a of f of x actually is, okay? So that classifies a removable discontinuity. Lastly, with an infinite/vertical asymptote, a limit we get an infinite/vertical asymptote if f of x does not exist because, the limit as x approaches a of f of x does not exist because we either get a plus or minus infinity as x approaches a from the left-hand side or a plus or minus infinity as x approaches from the right-hand side. So if you're working with a piecewise function and you get that a left-handed limit is equal to positive infinity or negative infinity, or same thing for a right-handed limit, then you're looking at a vertical asymptote, okay? So again, we're focused on the limit as x approaches a for vertical asymptotes to see if we get plus or minus infinity. So let's look at an example here. Determine if the function at right is continuous at x equals 2. If the function is not continuous, what type of discontinuity exists? This is a simpler example here because we're going to focus on more complex examples in class. Okay? So again, we can write our piecewise function using a number line. We see that for x less than or equal to 2, our function is 1 over x. We see that for x greater than 2, our function is 4 minus x divided by 4. So the first condition we're going to check right here is whether f actually exists at x equals 2, which means we just plug x equals 2 into f of x at x equals 2, which is 1 over x, okay? Which is just going to give 1/2. So we see that we have no problems here if first condition is met. Now if we look at step 2, the limit as x approaches 2 from the left of f of x is going to be equal to the limit as x approaches 2 of 1 over x. Again, 1 over x being to the left of 2, which just gives us 1/2. In fact, when we have this less than or equal sign, we could actually just condense step 1 and step 2 for 1 over x, since the function is the same for approaching from the left and for step 1. Okay? Now, as x approaches 2 from the right-hand side, we're going to use the limit as x approaches 2 for 4 minus x divided by 4. And as we can see, we don't have to do any factoring methods here. There's no problems. So we don't have to use any fancy or advanced techniques. So we get 1/2 as our limit. So as the limit from the left equals the limit from the right equals 1/2, the limit does in fact exist. So lastly, we see that the limit does exist. It equals 1/2. And by comparing with the function's actual value at x equals 2, we can see the third condition is also met. Thus, our function is continuous at x equals 2, which we see right here, but I can't bring it down because that sidebar is always going to appear. All right, so those are 3 conditions you always need to check. You cannot circumvent them. You cannot use any cheat codes, and we'll be spending class making sure we're good and strong on applying these conditions. Okay, so lastly, if we don't have a piecewise function, we may be asked to locate the discontinuities of a rational function, such as f of x equals x squared minus x divided by x squared minus 4x plus 3. In this case, to locate the discontinuities, what we do is we apply the same techniques from 1.2, where we factored the numerator and factored the denominator to see what factors we can to study each factor individually. So if we factor this, we're going to have f of x equals x times x minus 1 in the numerator, divided by x minus 3 times x minus 1 in the denominator. So if we focus on the factor x minus 1, okay, we can see that if we plug in x equals 1 directly, we're going to get f of 1 equals 0 divided by 0. So f of 1 does not exist. But if we take the limit as x gets closer to 1, by canceling out or removing the x minus 1s, we can get a limit here. Thus, we have a removable discontinuity at x equals 1. So removable discontinuity, when you're looking at these rational functions, is when you have these factors that you can cancel out on the top and bottom. Again, we plug in x equals 1, we get an undefined number, but we can cancel out the factors to get the limit, so we're going to get a removable discontinuity when we're able to remove these factors. All right, so now we move to the other factors, x minus 3. If we plug in x minus 3, we get 6 divided by 0, so f of 3 does not exist. Nor can we simplify the limit any further because there's no x minus 3 factor on the top. So what we end up having is a vertical asymptote, because recall from 1.2, a vertical asymptote occurs if our limit has some number divided by 0. So we have a vertical asymptote in this specific particular case at x equals 3. And then lastly, if we look at x equals 0, if x equals 0, f of 0 will just equal 0, which isn't interesting, but it's fine. So f is continuous at x equals 0. And these summarize our conditions for continuity and classifying discontinuities.